Welcome to the world of C++ type traits. In this video, we will explore compile time type information and transformations that you can perform using type traits. Let's define what type traits are. Type traits are templates that provide information about types during compilation. They have been a part of the C++ standard library since C++11. You can find them in the type_traits header file. Type traits enable making decisions at compile time based on the properties of types. Now let's explore the key benefits of using type traits. With type traits, you can inspect types during compilation. You can also use template metaprogramming techniques. It allows you to optimize code based on the specific characteristics of types and improve type safety, preventing errors in your code. Let's look at some basic examples of type traits. First, including the type_traits and IOStream headers. Create a template function called checkType that takes a value of type t. Inside this function, you can use standard is_integral to check if t is an integral type. If it is, the program prints is integral type to the console. Otherwise, if standard is_floating_point is true, indicating that t is a floating point type, the program prints is floating point. In C++17, variable templates are introduced, which allow us to directly use standard is_integral_v to check for integral types. This simplifies the syntax. Common type trait categories include standard is_array, standard is_pointer, standard is_reference, and standard is_class. Let's explore different categories of type traits. First, we have type properties. Is_const checks if a type is const qualified. Is_volatile checks if a type is volatile qualified. Is_sign checks if a type is signed. Is_unsigned checks if a type is unsigned. Is_abstract checks if a type is abstract. Next, we have type relationships. Is_same checks if two types are identical. Is_base_of checks if one type is derived from another. Is_convertible checks if a type can be converted to another. Is_constructible checks if a type can be constructed. Moving on to type transformations. Remove_const removes the const qualifier from a type. Remove_reference removes the reference from a type. Add_pointer adds a pointer to a type. Decay applies type conversions similar to those in function calls. Finally, let's see the type operations. Conditional selects a type based on a condition. Enable_ if conditionally defines a type. Common_type determines the common type of a set of types. Underlying_type retrieves the underlying type of an enumeration. Let's see how we can use SFINAE with type traits. SFINAE stands for substitution failure is not an error. SFINAE allows templates to be excluded from overload resolution if substituting template parameters results in invalid code. Type traits, when combined with standard enable_if, offer a robust mechanism for compile time function selection based on type properties. Here's how we can implement it with code. First, including the type_traits header. You can create a template that is only enabled for integral types using standard enable_if and standard is_integral. This ensures that the process function is only available when t is an integral type. Similarly, we can create another template that is only enabled for floating point types by checking if t is _floating_point. This directs the compiler to choose the appropriate function overload based on the type of the input. Now let's explore type transformations in C++. To remove references in CV qualifiers such as const and volatile, you can define a type alias named cleanType. It uses standard remove_cv and standard remove_reference to create a clean type from t. For perfect forwarding with decay, you can use standard decay to handle type conversions. For conditional type selection, you can define a type alias called numberType using standard conditional. This type will be double if T is a floating point type, and int otherwise. To add const to a type, you can create a type alias const type, which uses standard @_const. C++14 introduced shorthand notations for type traits using the _t suffix. For example, remove_ref_t is equivalent to standard remove_reference_t. Let's explore concepts in type traits, introduced in C++20. Concepts are named sets of requirements for template parameters. They offer more readability than SFINAE with enable_f. Concepts provide better error messages and are built on top of type traits. You can define a concept using type traits. Here's an example. Include the concepts in type_traits headers. Create a concept called numeric, which checks if a type T is arithmetic using standard is_arithmetic_v. You can then use this concept in a function template. This restricts the add function to only accept numeric types. Alternatively, you can use the requires clause directly, checking for arithmetic types using standard is_arithmetic_v. Let's explore real-world applications. Type traits are essential in generic programming with type constraints. They facilitate compile time optimizations. Also, they enable template specialization based on type properties. Type traits also enable static polymorphism with tag dispatching and prevent implicit type conversions. For optimized containers based on type properties, consider this example. Define a template class called optimized vector. Inside the class, use standard conditional to choose between a plain array and a standard vector for storage, depending on whether T is trivially copyable. If T is trivially copyable, use a plain array, otherwise use a standard vector. This kind of optimization leverages type traits to enhance performance based on type characteristics. Let's summarize what we have learned and explore some best practices. Key takeaways include the fact that type traits provide compile time type information. They enable template metaprogramming techniques. Type traits improve code safety and enable optimization. Type traits form the foundation for C++20 concepts. Now let's look at some best practices. Always use the _v and _t suffixes introduced in C++17 for variable templates and type aliases. Always prefer concepts over SFINAE when available, as they offer better readability and error messages. Combine type traits for complex conditions to create more specific constraints. Finally, always document your type requirements clearly so that other developers can understand them. To learn more, here are some helpful resources: the C++ Standard Library Reference, C++ Templates, the Complete Guide, cppreference.com Type Traits Documentation, and Modern C++ Design by Andrei Alexandrescu. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.